Okay, our next presenter before lunch is Matt Ruark. Matt is a professor and extension specialist at the University of Wisconsin. He holds an MS in soil science from the University of Minnesota and a PhD in agronomy from Purdue. Overall goals of Matt's research and extension programs are to improve nutrient use efficiency in grain, vegetable, organic, and biofuel production systems, and to reduce edge of field losses of contaminants from agricultural production systems. Matt?
You. All right, I'm going to try to move around a little bit. Okay, so thanks for inviting me. It's always good to be back in Minnesota. I also did my undergrad at the University of Minnesota, and I appreciate that. That was a nice tribute to George Ream. I worked for George Ream when I was in undergrad at the University of Minnesota. Spent a lot of time soil sampling, plant tissue sampling, and when I was a senior, I went to his office and just say goodbye, just thanks for everything. He's like, hey, Matt, you ever think about going to graduate school? It's like, what? No. Anyway, here I am. So George had a huge impact on my life, in a lot of ways. So we'll all miss George. So today I'm going to talk about cover crops and efficient nutrient management. This is a title that Fabian gave me. I give a lot of talks on the same thing. I'm joking, like I've got a whole other talk on inefficient nitrogen management. But what drives, so when we talk, so this is going to be talk on cover crops, but it's also going to be a talk on manure. So what drives cover crop research in Wisconsin specifically is this map right here, right? Number of dairy cows per square mile. You can see we got cows all over the state. We got a lot of counties in the state with a lot of cows. Right, so we have a lot of manure. This will, hopefully this is of interest to you, as we do have a lot of dairy cows here in Minnesota. Also a lot of swine manure. So how can we use cover crops with our, these other nutrient waste streams, nutrient waste streams to capture them? Let's try to get some benefit on both sides, right? We can have some benefits to water quality, but then can we also have some benefits with also more efficient nutrient use? All right, so one of the big things that we have that comes with dairy production in Wisconsin are corn silage fields, right? So we have these fields, everything's taken off. What a great opportunity for cover crops to be used, right? It's a great crop. About 25% of the corn in Wisconsin is used for silage, but leaves the field bare. Usually in this kind of case comes with a fall manure application. So we have bare soil, manure, nutrients being applied well in advance of the next crop need, right? So boom, great opportunity for cover crops to be used. So today I'm going to talk about some fall grass cover crops, their growth, nitrogen uptake, and also then their effects on the next year's crop. Okay, so this is a diagram I'm going to use, right? So we've got corn silage, right? We've got all this time period where we can grow a cover crop. And so we're interested in part one is what happens over the winter, how well do these cover crops grow? How much nitrogen do they take up? How much do they reduce soil nitrate? And then what do we need to do if we're following that with corn, right? So if it's a case where they're putting out a lot of manure in the fall, that's a lot of nitrogen. The next crop is probably going to be corn. How do we manage that nitrogen? So I just wonder if it's okay if I stand down here a little bit, look at the slides with you. All right. So we've got on the left here. This is a really fantastic stand of a winter rye as a cover crop. Survives the winter. It's a fantastic stand. I think we all can agree we like this more than this. There are trade-offs, so we're going to talk about them. All right, so I kind of use a general term of just a grass cover crop, and there's a couple different ones that we tested. So the first one is spring barley. I like spring barley a lot. It tends to grow a little bit faster. You get a little more growth in the fall, but it winter kills. So in a case like this is in the spring after it's winter killed. If you get enough biomass in the fall, you might have enough dead biomass coverage to get some soil protection in the spring. You might, right? But in a lot of cases, it kind of falls apart. But the flip side is you don't have to go out and spray it. So it's a great cover crop to kind of get started with. Annual ryegrass. So this one's tricky, where it sometimes survived the winter and sometimes didn't. Has anyone here worked with annual ryegrass, grown it? And so does it survive the winter here? It does. Fit this, yeses, seen some yeses. Okay. So we see in almost all of our trials, it came back like this, super patchy. And so it kind of fit in that in between where it's not, we couldn't get it consistently surviving the winter. So I know in Illinois, I think it's a little more popular. I think it does survive the winter a little bit better there. I don't know if it's just also maybe further north here, maybe. Anyway, I don't know. So we're just in a spot where it comes back a little patchy. So it kind of falls in that in between. And then we got winter rye. That'll survive the winter. So if you're looking for erosion control and some better, larger benefits to water quality during the spring months before planting, right? Winter rye is going to be the way to go. But, right, you got to go out, you got to manage it more, you got to go out, you got to terminate it. It's one more thing to worry about in the spring. But, so, pros and cons. So, here's a common setup here where we're going to work under a system where we're going to harvest corn silage, we're going to apply manure. In most of these studies, we're putting out about 10,000 gallons of liquid dairy manure. This will range in an available N application anywhere between 60 to, in some cases, 120 pounds of nitrogen in terms of potential. So that'll depend on a lot of things, right? So it's going to depend on the concentration in the manure itself, but then also sometimes, and the reason why that's going to be influenced is if it's a high solid content manure, low solid content manure, those sort of things. We're going to plant rye, we're going to terminate rye, then we're going to plant corn, then we're going to fertilize the corn, and we're going to harvest the corn, of course. So we're interested in, right, what's happening with the rye, and then how much, basically trying to answer this question, how much should we fertilize corn? So just to give you a sense of where our first round of research was conducted at our main experiment stations in Wisconsin. So in the southwest part of the state, just north of Madison, and then a little bit further northern Wisconsin. So we've got a range of locations with a range of applications of manure. You'll see that at one location, it was a separated liquid manure, so it had relatively low nitrogen content in it. All right, so a figure with a lot of lines on it. So we're going to go through one by one. It's a joke, just a little data humor here. Okay. What do we get? So on average, you can see, well, it's variable. It's always variable, right? So how much cover crop biomass you're going to get? I don't know. It depends, right? It's going to depend on the weather. But on average, we're getting about a little over 2,000 pounds of dry matter from winter rye. That's collected in the spring. Annual ryegrass was the lowest. Spring barley averaged about 1,200 pounds. So we're getting about half of the total biomass of winter rye with spring barley, just with the fall growth. The problem is not all falls are created the same. So if it's those nice long falls, we get a lot of biomass. If it's short fall, we don't get as much. Here's the interesting thing. I promise there's something interesting here. The winter rye, the average uptake in the above ground biomass was 54 pounds per acre. For the spring barley was 47, with only half of the biomass. It's kind of interesting. And the reason for that is that the C/N ratio of these cover crops is actually really low. So we think about grass cover crops as having a high C/N ratio, right? So we talk about legume cover crops or legumes having a low C/N ratio. It decomposes quickly, supplies nitrogen. Well, these ranges, with the spring barley is only about 10. So it's a more nitrogen-rich cover crop. That's why even with less biomass, it still has roughly, has a similar amount of total nitrogen. But in any case, we're in these ranges of 10 to 15, maybe a little more in some cases, of that C/N ratio. So like this is in the range where we're talking like, wow, we might get some nitrogen, might get that nitrogen back. Spoiler, we don't get the nitrogen back. But let's talk about why. So it gets to this idea too, right? It's about, there's still like an aspect of how plants decompose. And so it's not just the C/N ratio. We're planting these crops into an extremely nutrient-rich environment with the fall manure. So the C/N ratio is going to be low, but it doesn't mean you're going to get a nitrogen credit from it. All right, so a couple more pictures to put some things in context. the amount of biomass is what seems to be driving the show on how much more nitrogen to apply. So when we get a situation like this where we only have 500 to 700 pounds, this is kind of what it looks like. You know, a lot of soil coverage. So, you know, not a lot of growth. You might get a little erosion control out of this, but not a lot happening. Here's a picture of a field where we got about 1,000 pounds of dry matter biomass. So here we have, this is a nice number, 1,000 pounds. You have most of the soil is covered. Maybe you have a little bit of exposed soil looking down at it, but we have a nice stand. 2,000 pounds kind of gets to that range of where you've there's no more soil, no more exposed soil. And then you get to 3,000 pounds. We got 3,000 pounds 1 year, and where it's kind of a big, thick, dense stand of cover crops. So these are the two things to think about. 1,000 pounds, that's what about 1,000 pounds looks like. That's what 2,000 pounds looks like. And this is all on dry matter. And why does it matter? Because based on some previous research, this is from a paper, it's a meta-analysis. So they found every single study they could to try that connected cover crop use with reductions in nitrate leaching. And so what they found is this, in terms of the shoot biomass and the nitrate leaching, they found like it was relatively, and it's in metric, but you can think about this and, multiply by 1,000, and it's roughly kilogram per hectare is close enough to pounds per acre, right? We can use it. So this is the reduction in nitrate leaching. So you can see with even like a relatively small amount of biomass on average, you're still seeing almost 40% reduction in nitrate leaching. When you get to about a 2,000, you get to that, maybe 50% reduction. And once you get above kind of that 3,000 pound range, we're not really seeing that much extra benefit to water quality. So you don't really need that much biomass. You just need to have enough, right? And so this is a 500. There's a picture of closer to 500. This is a picture of closer to 2,000. So getting some growth is good. Will help you with your achieving some water quality goals. And that's also good news because we don't want the cover crop to get too big for agronomic reasons. Oh, this is just me saying, I don't know why they drew a curve. It's pretty flat right at the top there, but that's fine. I didn't review the paper. Okay, so back to this whole setup here. I repeated it also. Here we go. All right, so here's what I do then. So I put out, we have all that cover crop, and then we run a nitrogen rate trial, right? You've seen about 75 N rate curves at this point. Well, you're gonna see more. Okay. Here's what I do. So here's my, in the blue here, the light blue, that's following no cover crop. This is the nitrogen rate. This is corn yield. And in the dark blue is following winter rye. So right off the bat, you can see that the no cover had greater yields. And so we maximize yields with much less nitrogen following no cover crop. Actually, we needed 128 more pounds of nitrogen to maximize yield. I'll say, this is the worst case scenario. This was one of our studies that we did early on. We seeded very heavy with a cover crop. This was one that was well above 2,000 pounds of dry matter biomass. So we needed it took up a lot of nitrogen. It needed a lot to replace it. In addition, I had a 7 bushel yield gap that I couldn't close with nitrogen. So I needed a lot more nitrogen and had a little bit of a yield drag happening. All right, so we do this. This is the worst case scenario, and I have all these studies at multiple locations over time with a bunch of different cover crops. And so I'm going to use these numbers of the difference in optimum N and the difference to compare all these things. So what we can look at is, so this is the difference in the optimum N rate. Again, apologies for metric. Obviously, we're trying to work this up for publication, but okay. But kilogram per hectare is close enough to pounds per acre that we can make it work. All right, so if the value's positive, that means more nitrogen was required following the cover crop. And if the value is below, negative here, that means less nitrogen is required. So you can see for the most part, most values are either kind of on that line or greater, meaning that there was either a very small difference or much more nitrogen was needed. We graph that against the total cover crop biomass at the time of termination. So this is across all cover crops. So that would be the annual ryegrass and spring barley were sampled in the fall or right before winter kill, essentially. And then the winter rye was sampled in the spring. So positive relationship. not highly predictive. The R squared is only 0.24, so it's not like a highly predictive model. Like, but we can generally say that the times where we had above 2,000 pounds of dry matter generally had required much more nitrogen compared to no cover crop use. So what does that mean? So I couldn't use necessarily, I don't have an equation put together. We ended up putting them into kind of brackets, and it kind of worked when we looked at all the data individually. When we had less than 1,000 pounds of dry matter, there generally was no effect on the optimum N rate. So if you have less than 1,000 pounds of dry matter, I wouldn't recommend any adjustments to your fertilizer rates. When it was between 1,000 to 2,000 pounds, this is just a case when it was winter rye. I would subtract 35 pounds from your manure nitrogen credit. So if you're doing nutrient management planning, you're putting out the manure in the fall, that's going to get credited right to that next corn crop. Subtract 35 from that, right? Supplement 35 pounds more nitrogen the next growing season. And I put winter rye, here's the asterisk here. When winter rye was used, when we had spring barley in this range, no effect. When it was winter rye, we had this effect. Then we go to the above 2,000 pounds, which only occurred following winter rye, or with winter rye, I should say, right? And in those cases, it seemed to kind of wipe out the manure nitrogen credit. So cover crops are doing what we want them to do, where we think they're going to, right? They take up nitrogen. And I was hoping they'd be nice. They would just take up the nitrogen that was going to be leached out, over the fall anyway, over the winter. And they do that, but they also tap into the amount of nitrogen that was going to be available for the next corn crop. So is that a big deal? So fall manure applications are, they have to happen sometimes. There's only so much storage that can happen on some of these farms. If we can get that nitrogen trapped in a cover crop, I'd rather have it trapped in a cover crop, supplement a little more nitrogen the next year. To me, that's a potential win-win. So this is more of just something for fun. Just to remind that we're working with these low seed-N ratios, but we're seeing the opposite effect, right? We're seeing that we need more nitrogen with a low, and this, So as this cover crop is decomposing, it's not releasing it in time. You're not getting it back that year, right? And it seems to be independent of the seed-N ratio of the material. So the next thing we studied was, well, how do we try to keep the biomass below 2,000 pounds? Now we're working in a situation where, we're getting these cover crops. We can get them planted sometimes as early as mid-September, but a lot of times they're still like late September, even early October, and we can still get, if the fall conditions are right and the spring conditions are right, we can get 2,000 pounds of biomass pretty easily. So what we tried to do, well, how do we manage this? So a lot of the early cover crop work was done. We ratchet up those seeding rates, right? We wanted to get the growth. We want to get as much coverage as possible. We were using probably, how much should we seed? I don't know. What is the forage rate? So we use pretty high rates. So can we control this with cutting back on the seeding rates? And so the good news is we can, right? So here's our data. We've got 4 different seeding rates of rye, 30, 60, 90, and 120 in English units. Thank you. You're welcome. Okay. Finally, I did it right. But, right, what do we see? We see a slight increase, with the greater the seeding rates, more biomass. So if we cut back on the seeding rates, we can cut back on the biomass. The interesting thing that's here is that we had pretty good control. So here's our pictures on the right. When we look at the 30-pound rate, we're getting about 75% soil coverage. This is with that, Canopio app. We're looking at the percent green coverage, taking a photo, looking down. 75% soil coverage with the lowest seeding rate. Then it goes to 87, then it goes to 90, and it kind of tops out there. So really, all we're sacrificing a little bit, 15% coverage with cutting back on the seeding rate, but it helps us keep that number a lot closer to 1,000 than compared to 2,000. So I like that we can keep it. I think we can cut back on our seeding rates in a lot of cases and still have really good control. The other aspect of this is, what about the root biomass, right? So we were always measuring the above ground biomass, and I'm like, hey, we should sample the roots. And so we did, and by we, I mean my graduate student, we did a lot of sampling. We actually measured the root biomass as well. And you can see in some cases that root biomass was, 50 to 100% equivalent of the above ground biomass. Now, interestingly, the seed end ratio of that root biomass was much higher, right? So that's in a high, a much higher seed end ratio. So we wouldn't expect, that to necessarily be contributing any more nitrogen. But when we look at total N uptake, it actually adds quite a bit to the total N, that we're estimating that's taken up. In any case, so really, we're seeing, 62 to almost 90 pounds of nitrogen being taken up in the total plant biomass. That's a good amount of nitrogen, considering if we're expecting 60 to 90 pounds of manure being available when we apply it in the fall. Now, this is basically just to show that this is the effect on the soil nitrate. And so it's that soil nitrate, actually, the cover crops reduce soil nitrate. Less soil nitrate means you got to supply more nitrogen when you fertilize. But here's the more interesting graph. All right, so this is with all those seeding rates, including the no cover crop control here, right? We sampled to 2 feet in the fall, right before winter kill, in the spring at the time of cover crop termination, or in the summer. This was early June. We just kind of picked a time in season. And so the first thing we can learn is that the rye decreased soil nitrate in the spring. In the fall, there was a little bit of an effect. There wasn't necessarily a lot of growth yet. You can see a little bit effect there. Looking at these kind of middle blue numbers here, the rye decreased the soil nitrate in the spring. So significant reductions kind of in a pre-plant nitrate test. This is converted to pounds per acre at the time of planting, right? So to start, we're planting into a low nitrogen environment when you're using a cover crop. Okay, but the next thing is, and then it was not terribly different across all of the seeding rates. But when we look at the comparison of the spring to summer, and what I'm trying to get at here is I want to know if that cover crop is continually causing reductions in available nitrogen through immobilization. So the idea is this cover crop could be, as it's decomposing, those microorganisms could be stealing nitrate from the soil and using it for itself and not keeping it there for the plant. But what we're seeing is we're not seeing that happen. So compared to, we see a difference of 12 pounds per acre going from the spring to the summer when we're not using a cover crop. And in all other cases, the values were similar to slightly greater. So it's saying it's not having this cumulative effect of reducing the amount of plant available N during the season. The cover crop is just taking up the nitrogen. It's not, and it's just reducing the amount that's there. It's trapped in the plant biomass. It's not causing any additional in-season immobilization issues. And the reason why that's important is that it makes the equation a lot simpler. If it's just a matter of the amount of if we can say there's no real effects in season, it's just connected to the amount of nitrogen that's taken up, then we can just add back what's taken up. So we feel pretty confident with that. All right, the last kind of big concept here is, well, we got to talk about fall manure. And so fall manure is variable in terms of how much nitrogen it supplies, not only for what's there, but also is it going to stay there, right? So we're talking about a situation where we're putting out manure in early September in a lot of cases, trying to get as early as we can, get that manure out there. What's the effect? So this figure demonstrates, we can kind of go through it, but this relates, in all of these studies, I always had a comparison to no manure as well. So I always knew how much nitrogen the manure was applying. And so this is a case when the values are on this side of the equation. This implies situations where the fall manure provided a lot of nitrogen. You put out manure in the fall, it stayed put, so to speak, and provided a lot of nitrogen to that next crop. In those cases, right, when the manure is supplying a lot of nitrogen, the winter rye, the effect of the winter rye was very large. We had to supplement it a lot back. That manure was there. We should have expected a lot. When we compare it to the cover crop took it all up. We needed to supplement a lot back because it was a case where that manure was going to be there. Cases down here where the manure did not last over the winter, the effect of that cover crop wasn't very big, right? Because we have two things that are happening at the same time. We put out nitrogen in the fall, and if it leaches out, right, we have a low amount in the soil. Or we put out in the fall and the cover crop takes it up, we have a low amount in the soil. The net effect is the same. So in cases where that manure, you're going to have a big water quality issue because you leached out a lot of nitrogen because of the weather conditions, the net effect of the cover crop is the same. So it demonstrates that we do have to acknowledge it in some way and figure out how to account for it, but also we have to acknowledge that those fall manure applications, while it may be a way of life, and it's something we have to do, have a certain amount of risk associated with them. So I'm completely lost on time. 75 more minutes? Okay, good. All right. All right. Yeah. So I don't know. I have a couple other slides, but does anyone have any thoughts or questions or issues? Everyone agrees with everything I've said so far? All right. So we've tested a lot of this stuff at our ag experiment stations, and then the next step is, we've taken it out to farm fields to see if these things are currently happening, or things happening on farm fields in the way we're expecting from our ag experiment stations. And so here's some data hot off the press. Nitrogen rate on this axis, total corn yield on this axis, right? The blue is corn yields following not following a cover crop, and the orange is following a cover crop. This is a case where it was we were expecting somewhere between 60 to 80 pounds of available N through fall manure. We had about 1,800 pounds of biomass in the winter rye, so getting close to that 2,000 pound threshold that I'm afraid of. This is the amount of nitrate in the soil at the time of planting, or at the time of cover crop termination, excuse me. Quick aside, always 10 to 14 days between termination and planting, right? You're planting into a depleted nitrate environment, so if you have a setup for starter, definitely have nitrogen in the starter, get it going. And if you can, move your nitrogen application up a bit. If you're not using manure, maybe move that up a little bit to try to make sure that corn has that nitrogen as early as it can get it. Okay, in any case, we're seeing that same effect, right? Lower yields with less nitrogen. Clearly we need more nitrogen, but I'm not seeing, that big, I could close the gap with more nitrogen, right? So in terms of like it's suppressing yield, it seems to be just simply a nitrogen issue, just supplying back what was removed by the cover crop, right? So we had a difference of about, 70 some pounds here. This difference was in optimal N rate was, I think, closer to 90 pounds. So close enough for the math that we do. So it kind of works out, right? There's less nitrogen, we supplement it back, and everything worked out okay. With the goal, right? Working with the farmers that are interested in this, they're interested in having the cover crops there, right? They want to try to figure out how to make these cover crops work for erosion control and try to achieve some water quality benefits. Interestingly, we worked with another grower. This was a case where we didn't get manure applied. So it gives us a condition where we can actually test something without use of manure. So manure wasn't, they weren't able to get the manure applied at this. This is in northeast Wisconsin. There was about 1,200 pounds of biomass, but interestingly, this was a barley winter wheat mixture. And this was one working with a crop consultant in that region that he was really interested in, what if we split the cover crop, right? So what if not all of it survives the winter, only just part of it, right? So you get some biomass going in the fall, maybe half of it dies out. This was sampled in the spring though, and it was there was still a good stand of winter wheat left. So this is something that's quite interesting. There was a small difference, about a 24-pound difference in the total amount of nitrogen in the soil between the cover crop and no cover crop treatments. But as you can obviously see here, there wasn't a difference in the nitrogen response site. So we kept biomass low, closer to 1,000. So these numbers aren't magic, right? They're sort of guidelines of be closer to 1,000, not as close to 1,000. They were close to 1,000. The difference in the rate at the time of termination was relatively low, but good biomass and no negative effects in the system. So, what's driving this? Is it because there's not an excess of nitrogen in the soil because of the manure applications? Is it something special about the spring barley that tends to not have that negative impact? What is it? So to continue a lot of this work, I think there's a lot of great ideas that are out there for how to manage all this. All right, so take-home messages. First one's long. So cover crops are really the only way in our systems to get significantly reduce nitrate leaching with these late summer, early fall applications of manure. But it will reduce nitrate availability of the manure, which itself is a function of cover crop biomass and nitrogen uptake. So there's all these levers that are being pulled, right? Okay, so you put the cover crop out, you get erosion control, you get nitrate capture. You follow it into the spring, you got to supplement some nitrogen back. I guess I'll say the fact that we need a little more nitrogen isn't a bad thing based on the data that I've shown, right? It's using the nitrogen. So it's not unused nitrogen that we're putting out there, it's used nitrogen. Thus, the result of this is an easy fix. It seems to be part. It's a simple math problem. It's a simple, took up this much, there's a difference in this much, to supplement it back in our production, and we won't have to worry about production. But then the thing is, as I think about presenting to all of you, I don't know, is the idea of are these adjustments necessary? Do they always occur if we're not using manure, right? So as we think about systems, we have this cover crop use. I don't have any good recommendations we can talk through some stuff, but I don't know if we have any exact recommendations. I think that it's also a situation. So there's discussions about the PNT, and I should have probably asked how to use it. You cut me out. All right. Okay. Think. So you use it based on a ppm, and that's the adjustment. So we convert it to pounds per acre. But I think if you're in situations where you're expecting a lot of high PPNT situations, the cover crops will wipe that out. So it's sort of, these are sort of situations where it's a benefit only compared to what could have happened, right? What you could have got. So using cover crops, basically just work towards the higher end of maybe the recommendations. Use starter fertilizer, don't be short, but best we can, let's try, if you have situations where cover crops are really going to help you with erosion control and they're the key to your water quality, achieving some water quality goals, let's figure out how to use them. So with that, that's what I have for you today. Be happy to take any questions, thoughts from the crowd. Or we go online. Oh, everyone does it. Oh, everyone does it here. Okay. All right. So what stage was the rye terminated in the spring? So it says yield drag may be from lack of moisture rather than nitrogen uptake by the cover. Recommendations when to terminate. My recommendations to terminate are as soon as possible. Right, so we're not waiting for a growth stage. We're trying to get out at the best available field conditions to terminate. So you're right, based on my assessment, I think we, to try to achieve our conservation goals without hurting productivity, terminate as early as possible. You'll probably have at least 1,000 pounds out there if it's winter rye. Go ahead and terminate. Not a lot of value in trying to risk it to push it to be higher. So they were all terminated at, I suppose, various growth stages based on the weather conditions. But that's a fair point. Yield drag may be from the lack of moisture. So there were cases this year, right? We've heard certainly heard a lot of stories about rye doing very poorly following winter rye on some fields. Not all fields, though, interestingly. But we do have some cases where if a field's pretty drought stricken, yeah, the cover crop, it's going to be a nitrogen issue, and it's also going to be a water issue. And the bigger the cover crops get, the more water they use. So that is a fair point. All right. Will winter kill spring barley, annual rye, or spring wheat foliage? Okay. They increase? So will the winter kill of these things increase pea runoff in the spring versus a cereal winter rye that greens up in the spring? Okay. So this is a discussion about you have this biomass that's there, it winter kills. The cells rupture, perhaps there's a release of some phosphorus. And it's kind of there's some evidence that there's some cases where you can see a slight increase in the dissolved phosphorus that could leave. But for the most case, I think most cases, the net positive is exceeding whatever minor increase in dissolved P that would be occurring. So I personally am not terribly concerned about that being a water quality issue, especially if we're working under the condition of we're already putting out a lot of manure in these situations. But I haven't seen, this is always the case. This is always the case with these trade-offs. And I'd be happy to get some data if anyone had it, but it's not that it increases it, it's how much does it increase? Like, so is it increasing the amount that it's gonna matter rather than we know it's reducing nitrate, with all the nitrate take up. So what's having the biggest effect? That's the stuff to look for when we look at studies like that. All right, have you seen that increased nitrogen was needed in the 1 or 2 crop years after the cover crop seeded year? So unfortunately, no. So all of the studies that we're doing is we're looking at that single year effect, right? So the whole a lot of the focus on the study was cover crops with manure and that sort of adjustment. I would say that the idea is, a lot of the big question is, right, do we get that nitrogen back? The cover crop took up the nitrogen. Where does it go? And the answer is, well, we don't exactly know. The idea is anything that you can do long-term to build carbon in your soil, to build up some organic matter, to keep organic material in your soil system and build up the nitrogen mineralization potential of the soil is what's going to matter, right? So these are single year effects. They have to occur year after year, right? So if you can get a cover crop in year after year after year after year, after a certain amount of time, there is the potential, right, to have improved your soil. The corollary is that, so in North Dakota, they changed their fertilizer recommendations for long-term no-till, right? And that's because over time, they've done something to their soil to maybe build up this nitrogen pool, a mineralized nitrogen pool in the soil, and thus your soil supplying more nitrogen, you can cut back. No-till, you can do every year. Cover crops are harder to do every year. So using the cover crops as the lone method for soil health improvement or building up nitrogen in your soil, I think will be challenging. But we don't have a lot of data on long-term cover crop sites either. So that's one of our challenges too. Should there be an N credit for high biomass cover crop in year 2? No. Next question. Okay. So does everyone get that right? I think that it's taking it up. Doesn't seem to be, there's not going to be, I don't want to expect a residual effect. I think you go to managing, if you go, we're looking at the effect on corn, you're growing corn again, it's going to be your corn on corn rotation, follow your recommendations, but most likely, a lot of systems are going back to soybeans, so then there wouldn't really be a big effect. Is the lignin content of various cover crops independent of the C to N ratio? Yes, that is a good point. And could differences in lignin content be influenced by organic N decay? Right, so the whole difference is, why do we see a nitrogen credit when we use a legume cover crop? So I also have a lot of data. We look at red clover as a cover crop, right? We see that opposite effect. It's supplying 50 to 40, 50, 60 pounds of nitrogen. And that's the case. It's the physical structures of that plant material. Grasses have a little more complexity in terms of its of the biomass, and so it's just a little bit harder to break down. It requires a little more fungal activity to help break it down, so it just doesn't break down fast, even with the low C to N ratio. So yes, so I think yes, lignin is a good way to think about it. Anyone have a thought on that? Anyone disagree? Have a better explanation? Carl doesn't like my answer. I'll sit next to him over lunch. I've seen a couple of southern Minnesota studies that arrived at a 30 to 40 pound acre nitrogen scavenge from cover crop. Does your work align with this number? Sure, right? I'm looking at 60 to 90, but I'm getting a lot more biomass. So if in cooler climates, if you get half the biomass, it's about half the number. So I think that fits, right? I'm going to look to Carl for a shake his head for no, okay. All right, I think that's fair. Look here. Okay, here's another thing I didn't mention. I think should someone be cutting me off? I'm good on time. Okay. I've been going to a full biomass sample to get my estimates. The plant height, we were trying to see if we could get some estimates, just of biomass just based on height. But the seeding rate really threw that off because while we had lower total biomass with the lower seeding rates of rye, those plants were a lot taller. So the seeding rate is going to affect the height, right? Because all we're doing on a seeding rate, it's drill seeded, right? So all we're doing is changing the spacing between the seed as it goes down the row. So we're increasing the competition, right? So the height is a hard thing to use to calibrate. So I think we're going to have to, if you want to know how much total N there is there, I'd say go out, get a full biomass sample. If you can, send it to a lab, dry it down, get an estimate that way. But I think we have to go on a total biomass rather than a plant height for grasses. What happened to radishes as a cover crop? That's a good question. Where'd they go? Oh, well, okay. We studied this also in Wisconsin, but we really they need a little bit longer to establish well, and they winter kill, right? So they work well if you have maybe an early season vegetable crop. We grow winter wheat in Wisconsin, so we got stuff coming off in August. We can get the radish planted in August. It's a fine cover crop, establishes quickly, smothers everything. We do these kind of studies. We also weren't getting the nitrogen back, although it wasn't tying it up either. It was kind of a neutral effect. We did 9 site years with and without radish. Every curve was kind of right on top of each other. Wasn't tying it up, but wasn't supplying either. So I think they're fine for mixtures. If you're looking for something that radish can do, go for it. But I think there's other options if you're interested on the nitrogen side of things. Better to supplement with pre-plant or in-season N following covers with manure. So here's the thing where I don't have data to support this, but I would rather move it up. I'd rather move the nitrogen up into the season. Get the nitrogen out there a little bit earlier. If you're generally doing a side dress application, you may want to think about split applying it or moving it up. Generally, in the work that I've done, and this is based on the way I've operated, we go manure application, starter, and then we do a side dress application. So the nitrogen rates are based on a post-planting nitrogen rate. So moving it up a little bit, could that help? I think that it could. If I was starting with cover crops, I would want to do that to start until I got comfortable knowing if that was having an effect or not. But I think that would be what I would recommend without any data. So there, you take that into account. Would pivot bio be an advantage for an early season N to get the corn growing with a lack of nitrogen from the cover crop? Probably not, no. All right, so it was asked, and okay, I'll address it. I don't know. I have a hard time. There's been a lot of work done with pivot bio. So right, so this any sort of you're applying a bacteria that fixes nitrogen. You're applying it either as a seed treatment or an in furrow, and it's supposed to. Now we've got this population, this high density population of this bacteria that fixes nitrogen. It's a free living N fixer, right? So it's not associated. Doesn't live in the plant root like rhizobia does with soybean, right? So free living. That company, though, right? The idea behind it is that it's genetically, it's gene edited, so it doesn't regulate. It's supposed to not regulate the amount. It fixes N and then pumps that nitrogen out into the environment. It's not, and it doesn't stop that regulation. The natural free living N fixers stop giving away the nitrogen for free at some point. This is supposed to do that. Okay, so I love the idea in theory. I really do. But we just haven't seen a lot of studies in the Midwest. In Wisconsin, we completed 5 studies this past year trying to find how much nitrogen it might supply. And unfortunately, we haven't seen any potential benefit from it in terms of supplying nitrogen. So I think that there's a lot of how do I say it? It's an ecology issue, right? So you have these things that are living in the soil environment. How do they thrive in a way that it's going to keep supplying nitrogen? So I really think a product like this would have tremendous, it would have huge implications for agriculture if we can get it to work. But I think there's some ecology related issues that we need to work through to keep it surviving and supplying nitrogen. Is that it? Okay, thanks everyone.